So my presentation will be on assessing water productivity and other irrigation performance indicator using Python script. In fact, this is a follow-up from the previous two webinars. In the first one, we introduced the concept, and the second one also we showed what kind of indicators we could derive from the WaPOR dataset. And in this one, we'll try to answer how we could calculate those indicators. So this, of course, will be built up on the download data, as Vic already explained. As Vic already explained, then we will show the first step, which is pre-analyzing the data. As some of the layers are coming in larger or coarser resolutions, so they need resampling. For instance, a reference evapotranspiration or precipitation, they need to be resampled or scaled down to the scale that fits the highest resolution WaPOR data we have, either level 1, 2, 3, that is 250 meter, 100 meter, or 30 meter, depending on what we have on the ground. And then again, the other thing we could do as part of the pre-analysis is masking out crop or non-crop areas. And as part of step 3, then once we have those corrected and prepared data, we calculate the seasonal water consumption or production. Consumption related to potential, actual, or just the productive evaporation or the transpiration. And as part of step 4, we calculate the seasonal, so based on the seasonal water consumption, then we calculate the irrigation performance indicators that include water consumption, beneficial fraction, equity, adequacy, relative water deficit, and reliability. And as fourth step, we calculated productivity. So the productivity includes both land and water. And as part of fifth step, then we try to identify the productivity targets. So the productivity targets, as we defined before, they are values compared across all the space in the project area, and which are in the highest percentile. And in fact, we defined when only both water productivity as well as biomass are the highest, then that place or spot is identified as a bright spots. And then as part of, again, the fifth step, we try to identify where exactly that bright spot is located within or across the project area. In fact, we did this systematically. So starting from downloading up to the whole analysis, and then, as already Vic explained, we developed a standard protocol for those analyses. And those protocols can be downloaded in our GitHub repository, which is wateraccounting/WaPOR. And it's freely available. And I'm going to walk you through that, how you could go from step 1 up to step 5. And I will share now my second screen, which will show that in the Python script. So do you see, I hope you see my screen, right?
Yeah.
Thank you. Okay, so the link is already explained, shown in our previous presentation. It's wateraccounting/WaPOR. In this link, you get all the scripts and also the data. And in fact, if you want to use this one, there is a nice, precise explanation, which is in the README file, how to go, or what are the definition, and also how to go through each steps. And in fact, what let's say, package to download and install, and also even how to install them is already explained here, and also by my colleague Vic in her presentation. So now, let's say once you have this one, then you need to download this, and then you can work on that one. So now I'm going to show you how, because once I already have the downloaded one here, then how will you do the analysis? So if you click, then after downloading, this is what you are going to find. So you have the data. So these are the data. The shape file are around here in this folder. And then the reference, actual ET, and transpiration and net primary production, those are the download data, which are named or started with 1. But the others are with 2 and 3 are going to be calculated, and I will show you how we will calculate. So the notes or the scripts are in the notebook. In the notebook, then you could open Jupyter Notebook either through the command book prompts or directly if you type Jupyter Notebook, then still Jupyter Notebook can open for you here. So then we have this Jupyter Notebook. This already explained by Vic. Then I will start from the first step. So the first step is about resampling. As I said, there are 2 activities that we will undertake in this step. So the first one is resampling and masking out non-crop season. And as it's already explained, we need to import either standard libraries or modules that we already wrote. So there is a module that is adopted by our group, and then this is from where we are downloading, but then the others are standard library, and then we need to import them. So I first import that, and again, I import all the data to be resampled. So my data to be resampled in this case is just to reference evapotranspiration. So I will then import it, and then these are the data. And then I create or I indicate the folder where I want to save that resampled data. So here I gave a folder name, this one, 1L, 1RET, then indicator 1. So yeah, whether we create it or whether we have that folder also we can see it. For instance, in my folder, in the directory of C, then I will get it in the folder of Vapor, WP, data, and this one. And then the resampling needs to start. It may take some time, that's why you see here the start, and also a dark spots at this point. So when it's finished, it becomes white one. So at this stage, we can see, for instance, the size of and the shape of the resample data. So the size and the shape of the resample data is now 151 row and 250 columns, or the total file name is this much, it's about 7,000. And the second step is, in fact, filtering non-cropped area. So there is a land classification map in Vapor, and this is how the numbers in the class are how they are classified. And the ID indicates, for instance, 42 is cropped or irrigated land. So in my case, I want to do only the analysis for the cropped land. Then I will filter out all the rest and then retain only the pixels which have a land class 42. So this is first importing the data. So the template data, I need to use a template data with which I can do the filtering. So for instance, I want to filter out from the actual evapotranspiration data. And then if I plot just the whole boundary of my project area, this is how it looks like. But then before removing or filtering out the non-cropped data, the actual evapotranspiration look like this one. So it's beyond the project area. Even in the project area, there are spots where there is no irrigation or which are settlements, for instance, in this area, but they are there. So I want to filter out those, and that's then the step I did in my previous, and then here I could show you in the picture also. So this one is, in fact, after filtering out then the irrigated, the non-irrigated area. So you see that now all non-irrigated area are removed, but still there are areas which are part of the analysis. And again, I want to remove all of them which are outside my scheme, because my scheme is somewhere, it looks like this one. So anything outside this and even in between should be removed. So in this step, then that's what I'm doing. Then this code does that. So this is the first step. And the second step, once we have a clean data, is about analysis. So the analysis will be, in our case, the second step, the step to be analyzed in this case is the seasonal water consumption and production. That includes seasonal actual evapotranspiration, seasonal transpiration, seasonal reference evapotranspiration, and seasonal net primary production. It's already shown by my colleague using QGIS by Sajid, but now I will do the same, not for one season, but for multiple seasons, just with a click, just using the script we have here. So the first thing is importing the libraries. The libraries functions which help me to calculate, and the second, or to analyze. And the second step is again importing all the data which I want to do the analysis of. And in this case, I need to communicate with the Vapor, because when I let's say when I add the rasters, then the script needs to identify if the rasters fall within that crop season or not. When we download from the Vapor database, there is already around it, so by its name. So the name, for instance, here is level 2, actual evapotranspiration, and 2009, and the first decade, which is T5. Then for that reason, I need to communicate with the Vapor API, the modules that Vicky explained. But in this case, and always if you use this script, I will recommend you only to run this once, because when you run it, then it saves already automatically in your computer with this name. And it is, in fact, saved here. In the data, all the names here are the saved one. So once you saved it, then the second time you need to just use or read from whatever you saved. And in this one, I will just read whatever I saved before. And then here, I will create a folder. So the folder where I want to save the seasonal transpiration, actual evapotranspiration, and net primary production are named with this folder name. So they are now created already. And this function, in fact, adds all the seasonal from the starting to harvesting. And for that, in fact, it uses planting date and harvesting date. And I will explain in a bit where you will edit your own planting and harvesting date. So the planting end, or the starting and end of the crop season, it's already in the Excel file. I saved it with SOS, EOS, which is starting of season and end of the season. And I will show you where I have it in my folder. In the folder, in the data, at the end, you see here the seasonal starting and ending of the crop season. If you open this Excel file, of course, you can edit the planting. Well, I should just open it. Okay, well, until it opens, then I can continue. So those planting and harvesting dates, Then if I run it, then it reads from the Excel file. So it means I will use those planting seasons. That is from 1st of October up to end of September. That is along all the years from 2009 up to 2018-19. Then we start to calculate the seasonal. For instance, the seasonal transpiration, if we click, then it saves it in a folder because we are giving the folder where it has to be saved, and also it plots it here. And similarly, we can calculate the seasonal evapotranspiration. That is just for the whole season. So you might see here it's busy because it's calculating, and it adds the graph. And then just within a click, we have a seasonal actual evapotranspiration of the whole 10 years. And similarly, for reference evapotranspiration, the same can be done. And the final seasonal for crop production is the seasonal parameter I want to calculate is the net primary production. And then again, this can be just calculated through the same, just clicking. And of course, you can do the same. I mean, that is also the idea of you can use or modify this script to calculate the seasonal water consumption and evaporation. So the third step is calculating the performance indicators. So the performance indicators in this case are water consumption, beneficial fraction, equity, adequacy, relative water deficit, and reliability. And you could read about those. In fact, they were already explained in our previous 2 webinars, but still you could use some of those references, and also from the README file that I show you from our GitHub repository, what they mean, and also how they are calculated, all the equations. And again, we start to import all the equations, the functions, the standard libraries in the Python. And then, of course, the first one is calculating the equity. So equity is explained as a coefficient of variation of the actual evapotranspiration across the whole area. And then if we want to calculate, then it can be also saved. These are the values. So for each, when I printed, so for each season, 2009/2010, these are the coefficient of variations for different years. And in fact, if they are fair or poor, those indicators are also mentioned here. And again, as I said, from the reference, you could check what I mean by fair, uniform, or not. And the third things to calculate among the indicator is the beneficial fraction. Again, for this one, we need input of transpiration layer and evapotranspiration layer, which are the actual, and across the whole season. First, we read and we import those files. And in fact, if we want to see whether we import them or not, this is actual evapotranspiration, and this is the transpiration. If I run it, then I can see, yes, I'm downloading 10 season transpiration and 10 season actual evapotranspiration. And then first I specify the output folder where I want to save. Then in this case, I named it 3 beneficial fraction. So that is the folder where I want to save it. And then if I run it, then it means this is the folder and it is created. And if I want to know whether it's created or not and where I have it, then I just can run also after including this name. Then it will be in the data with the name 3 beneficial fraction. So then I will calculate again the seasonal beneficial fractions, and then I can save it also in the folder. So if I run this one, you see the beneficial fraction maps for the 10 seasons. The other parameter is, or indicator is actual adequacy. It's calculated with this formula, which is actual ETA, seasonal over seasonal potential evapotranspiration, and the seasonal evapotranspiration, as explained by my colleague Sajid, is average Kc, that is a weighted average, times the reference evapotranspiration from the season. So since we are talking about seasonal layer, then this has to be averaged over the season. As you could see here from the graph, the Kc varies along the crop stage. So initial development and the mid-season, late season. So we weighted based on the value, magnitude of Kc, as well as duration of each stage, crop stage. So I think this formula explains. So to do that, then after calculating for sugarcane, we got 1.045, and also we need to import the other parameter, which is actual ET and reference evapotranspiration. And then again, similarly, I will specify or create a folder where I want to save the adequacy. That is what is being done at this step. And then finally, I can calculate and then I can plot. I will show you how the calculation is done. So in fact, the whole script here is just import and then do the calculation and then save it in the folder and also name it with the name adequacy. So if I run this one, then we start to generate the map at the same time saving the whole folder, the whole layers in the folder. And in fact, we can also plot this along the time, just averaging one value per area. And then I can show you here, in fact, this script is doing that. So the adequacy for each season, and of course comparing with the good performance acceptance range and poor performance are again plotted. And the other indicators I have in this step is, in this step 3, is calculating relative water deficits, which is 1 minus actual evapotranspiration seasonal over the maximum evapotranspiration seasonal. Again, I import the input data which I need to calculate this, and then using this script, then we can calculate automatically. It's very quick. So with this, I will go to the fourth step where I would calculate the productivity. That is another indicator. So we have productivity, that's the biomass productivity, and also biomass water productivity and the yield. So in this case, if I use harvest index, then I can talk about crop yield. Otherwise, without harvest index, I'm going to talk the biomass. So the biomass over the actual evapotranspiration is defined as biomass water productivity. So again, I start importing libraries which I need to calculate those indicators, and also input data or layers to calculate the biomass or the crop yield. So that is the net primary production. So I collected from this folder, and then again I create a folder where to save those layers or those analysis. Now I have the biome 4 L2 biomass. Of course, you can give your own name, it doesn't matter. So it means this is the way to calculate it. The biomass is, we have the net primary production, the seasonal one. First, we need to transform it into the dry biomass by multiplying by 22.22, and then from the dry biomass into the fresh biomass by dividing or correcting by moisture content, and then multiplied with a factor. For instance, if the crop is C3 or C4 crop. And in our case, sugarcane is C4 crops, then we use a value 1.8, which is to transform a light use efficiency, which is used in the NAPP, in the net primary production calculation in vapor, which is for C3, into the C4 crops. And then finally, we multiplied with above ground to the total biomass ratio. So these inputs are needed. Then if you want to run this script for another crops, you need to change those crop parameters. For instance, for sugarcane, we have a value of 0.8 or 8% of the total biomass will be above total biomass. And as I said, this is 1.8 for C4 crops, and for C3 crops, it's just 1, because the whole layer NPP in vapor is calculated assuming it is CC crops. That's why we just use 1 if it is wheat, for instance. But for C4 crops, then we need to change those parameters. And we have a moisture content. For instance, this is a value we got from an experiment one of our students did as part of his MSc in sugarcane production in Wanji. So we have this, we just use that value, 0.59. And the harvest index, we use 1 if we wanted to talk about biomass. But if we want to talk about harvest, a marketable yield, then we have to change this into the appropriate harvest index. And maybe in our repository, we will add some of those parameters for other crops. So we need to import those parameters because I want to calculate for sugarcane, and then I can calculate the biomass for sugarcane. So now you see it's being calculated and saved in the folder that I created. And similarly, we can import and calculate the water productivity. This script does that one. So I can just quickly run because it doesn't take much time. Once you have the script, then it means at the end you have the water productivity map. So my final step to explain is how we could identify the bright spots, and also how we could calculate the target, productivity target, and also identify bright spots. And also finally, if we want to calculate a productivity gap, how we could do that one. So again, I will start just importing the modules and the libraries which I need to calculate, and then I also import all the input data which are needed for that. It's actual evapotranspiration, biomass, and biomass water productivity. And then I will calculate the target's productivity. The target productivity is defined as 95 percentile of the productivity. So it means for biomass, 95 percentile of the biomass across the space will be the target biomass. And similarly for the biomass water productivity. So I could use this function to calculate the target. It means now it's already calculated. Then the target value can be calculated like this. So targets impacted biomass and target water productivity are this one. And also if I plot just for one season, it look like water productivity in the y-axis and then the biomass in the x-axis, and then this one will be the target one. So this is for one season. But then, I mean, this is also the distribution functions. And then when we talk about this point, it is around this value. But then all points beyond this one can be identified as a bright spot. And this one, this function will do that one. It will try to find exactly where this bright spot or this spot will be located in our geographical area, project area. So it's now for each season where the biomass is greater than 95 percentile are the green areas, where the water productivity are greater than 95 percentile are again scattered with the red one, and the combination or the intersection of the two are now shown in the spots. So those are areas which have higher biomass and higher biomass water productivity. And in fact, we can trace across all the seasons, and also we can identify which location is really a bright spot, and from where we could learn the management, the smart management which is going there can be replicated for other areas. And then, okay, if we identify these targets, we can also calculate the gap. That is the productivity gap by comparing what is the target and also what is the actual per each pixel. Then the last function is doing that one. So first we calculate first we create the folder where we want to save the productivity gap, and then the biomass gap can be calculated while being saved in the folder, and then it can be calculated. So this map shows for 10 seasons what are the biomass gap. And then similarly for water productivity gap. This is biomass water productivity. So with this one, I'm close to finish, just only showing you now where are those results in the folder. So it means now you could see I have already those folders, 2, 3. If I open them now, I have 10 seasons where everything is calculated. So feel free to use this free GitHub. I mean this script, and yeah, come to us if you have a question. Thank you very much.